Okay, welcome back. Welcome to the complexity and coding theory session. We'll just jump right away with the first talk. Ron is giving the talk about local proofs approaching the witness length.
Thanks, Elena. So as Elena said, this work is about local proofs approaching the witness length, and it's a joint work with Noga Ronsvi. So the starting point for this work, and maybe it's a good starting point for this entire session, is the notion of a probabilistically checkable proof, or a PCP, that you're all probably familiar with. But let me remind you anyhow. So a PCP is a way to take some arbitrarily complex proof and encode it in such a way that the encoding of the proof can be verified by reading only a very small number of bits. Right, so PCPs are not just a cool notion, they actually exist. So the widely celebrated PCP theorem, proven by Roland, Motowani, Segedi, and Sudan back in the early 90s, following a sequence of works, and there's been a ton of work since then. But what the PCP theorem tells us is that you can take any traditional empty proof and encode it in such a way that the encoded proof is only polynomial factor larger, and you can test this encoded proof only using a constant number of queries. So really an incredibly remarkable result. And not only is it remarkable as a statement, it's also been really transformative on our field. So first of all, in terms of complexity, it's kind of had an amazing impact on the field of hardness of approximation, kind of rewritten a lot of the field there. It's been used to derive circuit lower bounds works by Ryan and others, Karp-Lipton style theorems. I believe we'll hear about more complexity implications in this session. It's also been extremely useful in cryptography, where it was used to build succinct argument systems. So these are proof systems that are computationally sound with incredibly efficient verification. They've been used to do things like non-black box zero knowledge and so forth. And lastly, and I feel that this is really remarkable, in the last 5 or so years, PCPs and really generalizations thereof that we'll talk more about in this talk are actually being implemented, and it's become a multi-million-dollar business and industry. So there are startup companies who are working on implementing PCPs, which is pretty remarkable. So this talk is going to be about short PCPs. So let's kind of dive right into that and look at what is the key question here. So suppose that I give you some language L that you can compute non-deterministically in time t. Can you construct a PCP for this language with only a constant number of queries, and so that the proof length is only a constant times t? Okay, so only constant overhead. So this is the question, but actually it's not clear that this is the right question, because this question framed as is really very much dependent on the computational model. Because when you switch between computational models, number of tapes and so forth, then you usually have some logarithmic overhead. And here I'm really talking about constant overhead for the PCP proof. So an arguably better question, but certainly the question that the community has kind of settled on, looks at Boolean circuits and kind of asks this question for Boolean circuits. And you can frame it as asking whether circuit SAT has a PCP with constant query complexity, and where the length of the PCP is linear in the size of the circuit. And if you don't like Boolean circuits, then you can still use this to get PCPs for Turing machines with just a single logarithmic overhead. And I think it's a really natural question to ask, what is the best overhead that you can get in terms of the proof length? And beyond that, it has concrete motivation. So first of all, for this application to cryptography, getting succinct arguments, this would be very beneficial. And actually, there, the bottleneck is not in terms of the length of the PCP. It's really in terms of the time that it takes to construct a PCP. But of course, the length of the PCP is a lower bound on that. So if you want efficient provers, you better have short PCPs. So that's one motivation. The other is to the field of fine-grained hardness of approximation, where you really kind of need optimal parameters for your PCP to derive kind of results that we would like to have. So what is the state of the art here? Well, it turns out that it's very, very close to what we would like. So, and it's been this way for the past kind of decade and a half. So if you combine works by Ben Sasson and Sudan with the gap amplification of Dinur, that would give you a constant query complexity and proof length that is only has kind of polylogarithmic overhead. So overall kind of quasi-linear in the size of the circuit. Okay, so really the ball game is going down from polylog to a constant. If you insist on kind of a linear proof length, then a work by Ben-Sasson, Kaplan, Koparty, and Meir would give you this, remarkably, would give you linear proof length, but the query complexity is very far from what we would like it to be. So it's n to the epsilon, and the proof length has some very large dependence on epsilon. Okay, so we're not going to solve the problem of short PCPs today. Rather, we're going to look at a relaxation of the notion of a PCP. And this relaxation is known as an interactive oracle proof. It was introduced in two independent works a couple of years ago. So one was by Ben-Sasson, Chiesa, and Spooner, and the other was a joint work together with Omer Reingold and Guy Rothblum. And this notion, you can think of it as a kind of a hybrid between a traditional interactive proof and a PCP. So the way that it works is the following. We have this kind of setup like an interactive proof, and the prover sends over a PCP string. Now, given this, the verifier doesn't just stop here. The verifier is going to kind of send a question to the prover. Now the prover is allowed to send another PCP string, and so on and so forth. At the end of the interaction, the verifier can decide a few bits to read off of each message. Okay, so this is the notion of an interactive oracle proof. And at first glance, it may seem a little bit strange. Why can you send these long proofs and not charge for getting them? And I want to set that question aside of whether it's natural or not, because the point is that it's an incredibly useful abstraction. So in our work with Omer and Guy, we use this in order to construct a new double efficient interactive proof. So interactive proofs where both proving and verifying are highly efficient. And it's been used in the work of BCS and a sequence of follow-up works to construct highly efficient argument systems. Okay, so we're focusing on this notion of an interactive oracle proof. And turns out that using this relaxation, we actually know how to get constant overhead. More specifically, a work by Ben-Sasson et al. Constructed an IOP for circuit SAT with constant query complexity. So the number of bits that the verifier eventually reads is constant. And the communication is linear in the size of the circuit. So borrowing terminology from coding theory, the rate of this IOP, which is the size of the circuit divided by the communication, is a constant. Unfortunately, it turns out that this constant, the rate here, is very close to 0. So it's somewhere in the order of 0.001 or less than that. That's an upper bound. And our main result is kind of a high rate IOP for circuit SAT. So we show that circuit SAT has an IOP with constant query complexity, but where the proof length is just 1 plus epsilon times the circuit size. Okay, so just kind of additive overhead on top of the size of the circuit, which is the original kind of NP witness. And in terms of rounds, the number of rounds of interaction is kind of a small constant, but it's a slightly larger constant than that in the previous work. So that's our first main result. To state our second main result, I kind of want to stare again at this question of length of PCPs. So let's look for a second on SAT, say SAT with n variables and m clauses, CNF SAT. So the length of the NP witness, of course, is just n. But if you look at the length of PCPs and IOPs for this, then they always correspond to the non-deterministic verification time, which in this case is kind of has an m factor baked in. So that would give you, even the best PCPs and IOPs would give you kind of O of m or O tilde of m. And a natural question is, can you have a PCP where the dependence is just on the witness length? So unfortunately, the answer turns out to be no. So this is a work of Fortnow and Santanam, and under reasonable complexity assumptions. But by introducing this relaxation of IOPs, you can derive from a work of Kalai and Raz an IOP for circuit SAT with just poly m length. Okay, so no dependence on m. And in this work, we improve the state of affairs. So we show that for a very large class of NP relations, namely any NP relation that can be verified in polynomial time and bounded polynomial space, we construct an IOP with constant query complexity, but where the length is almost the length of just the witness, the unencoded witness. So 1 plus epsilon times the length of the witness. And in terms of the NP languages, the way we capture problems like SAT, clique, homotonicity, TSP, basically all of L21 of Karp's original NP complete problems are captured here. And also the length here is kind of optimal under the randomized strong exponential time hypothesis. So I want to say just a couple of words about the techniques. So a key challenge that we face is that all prior works on PCPs and IOPs utilize something that's called a multiplication codes. Which you can think of as codes where if you take two code words and you take their pointwise product, what you get is still some kind of code word. So a good example is Reed-Solomon codes. And these are very useful for constructing PCPs, but the problem is that the rate of these codes is not so good. In particular, it's at most half. So we cannot use multiplication codes in the traditional way. And indeed, what we do is to encode either the computation for theorem 1 or the witness for theorem 2 using a high rate code, a high rate tensor code. But then we emulate queries to some low rate multiplication code that's just in our head. We emulate the queries to that using queries to the high rate tensor code and additional interaction with the prover. Okay, so that's what I want to say in terms of techniques. Let me just conclude with some open problems. So the obvious open problem, can you get kind of constant rate PCPs for circuit SAT? And one reason for hope is that we can do this. We can do much better than we know for PCPs for LTCs, for locally testable codes. Alternatively, we can get a high rate PCP with any non-trivial query complexity. Second, can we use these short IOPs to say anything about hardness of approximation? I think that's a great question, and I have no idea. Thirdly, we have this limitation to bounded space NP relations. Can we remove it? Can you show that it's inherent? And lastly, can we use the fact that we have these shorter proofs to also improve the prover running time? And in a very recent follow-up work of Boodle, Chiesa, and Groth, they indeed showed this. So they constructed IOPs in which the prover can be implemented by a linear size arithmetic circuit over some sufficiently large field. So I'll end here. Thank you for attending. And if there's time for questions, they're most welcome, or if not, then please ask me after the talk.
Yeah, thank you. There is time for questions. So you can either just unmute yourself or type it in chat.
I have a question. Hi. Can the proof length ever be 1 minus epsilon times n? I mean, the length of the IOP and the size of the circuit are different. They're in different units. So I mean, maybe the proof length.
Again?
Could the proof length be 1 minus epsilon times n? For an IOP, is there some reason why it can't?
Yeah. So we believe that. So there are results on kind of laconic provers that interaction should not let you solve NP-complete problems faster or significantly faster than NP proofs. Okay, so kind of I was alluding that under the randomized strong ETH, you would not be able to do that.
Okay, thanks.
More questions?
Maybe I missed that, but did you say anything about the number of rounds in?
Yeah, so number of rounds is constant. It's so I don't have it on top of my head, but I believe it's in the ballpark of 8-ish. So not a terrible constant. I think the prior work had a couple of rounds less than that.
Is there any hope of, like, when you work on IOPs, do you ever think maybe I'll get a PCP out of it? Like maybe I'll manage to lower the rounds to 1, or?
Hope, yes. Materializing the hope is a different thing. So we're really very much utilizing this extra power that the additional interaction gives us. But, and indeed, at the end of the day, we do use multiplication codes, but we don't use them explicitly. And I don't see a way to do that if I'm restricted to just doing the PCP.
Thanks.
Can I ask a quick question? Do I have time?
Quick question. And
okay.
Maybe we can let the next speaker just
Sure.
upload the slides meanwhile.
Sure. Yeah, so my question was about the query complexity for 1 plus epsilon. Does the query complexity depend on the epsilon, or can you take epsilon subconstant and still get?
Yeah, you can. So you can take it to some subconstant values, not small as you'd like. The dependence would be poly 1 over epsilon, but if I'm not mistaken, at some point it won't there's a problem. But for some subconstant values of epsilon, you can do this with poly 1 over epsilon queries.
Thank you.
Okay, let's thank the speaker Thanks, Ron. Or you are the next speaker, right?
Yeah.
So the next talk is on rigid matrices via rectangular PCPs, and Or will be giving the talk.
Thanks, Elena. Yeah, so welcome everyone to the short and fun version of the talk about rigid matrices and rectangular PCPs. This is a joint work with Amey, Prahlad, and Avishaj. I think are all on this call. It's really cool. So what's the plan for the next few minutes? I'll introduce rigid matrices, just remind everyone what that is, or if this is the first time you're hearing about it, great. Then I'll say what our results are regarding rigid matrices. Next, I'll introduce the new concept that we study, rectangular PCPs. This is the main new concept in our work. And lastly, I'll try to sketch out the connection between rigid matrices and rectangular PCPs. Okay, so let's go. What are rigid matrices? So a matrix is rigid if it's far from being low rank. So rigidity is parameterized by a rank, rho, and a distance, delta. And a matrix is rigid if not only its rank is high, higher than rho, but also to lower its rank down to rho, you need to change a delta fraction of its entries. So it's kind of like a robust version of high rank. So it's parameterized by rho and delta. And matrix rigidity has kind of cool, surprising connections to other areas of computational complexity. The first connection, I think, was shown by Valiant in the 70s. So in this really cool work where Valiant showed that the linear transformation underlying a rigid matrix or induced by a rigid matrix cannot be computed by circuits of linear size and logarithmic depth. So basically, this kind of means that if you have explicit constructions of rigid matrices in some class, you get circuit lower bounds with respect to that class. And there's other connections, which I won't be able to talk about right now. Okay, so we saw kind of a formal definition of rigid matrices. I'm going to give an intuitive view, which will actually serve us in a little bit. So we have a matrix. This is this gray rectangle. And we know that if the matrix is low rank, then it can be decomposed into the product of a very narrow and tall matrix and a very short and wide matrix. So in that sense, low rank matrices, you can take n square bits and compress them into n times rho bits. Think of rho as like much smaller than n. And we also know how to recover efficiently an entry in the original uncompressed piece of data, right? It's just the dot product of a row and a column. So in this sense, rigid matrices are not only are they not compressible, they're not even approximately compressible, okay? So we want explicit constructions of rigid matrices, for example, to get circuit lower bounds. What are some constructions? So by a counting argument, a random matrix is very rigid, but that's very not explicit. So there has been a sequence of works throughout the years that get better explicit rigid matrices. So maybe they're have faster running time or better rank or better distance. I won't be able to talk about any of these, but I will zoom in on this last most recent work before this one, which was shown 1 year ago by Josh Allman and Lijia Chen here at FOCS. So if we take a look at the parameters, we see they had constant distance, which we think of as wonderful. I'll talk about the rank in a bit, but what I want to highlight is that their construction is not explicit in the traditional sense that we mean, a polytime algorithm runs in poly n time. It also uses some non-determinism, okay? So it's efficient, but uses non-determinism, kind of somewhere in between. Well, if we have their parameters in mind, then it's really easy for me to say what we did in our work. We constructed rigid matrices that still have constant distance. They're still in this explicit with non-determinism runtime. And we managed to improve the rank from there 2 to the log n to the quarter to 2 to the log n over log n. So if you like graphs, this is a graph of how the rank is different. And let me pause and say something. Both of these constructions only work for infinitely many n. So that means you don't get rigid matrices of any size you want. You only get, eventually larger and larger rigid matrices. So that's definitely a pretty lame thing to say right after I introduced our result. But fortunately, in this very same conference, Chen, Liu, and Williams just improved both of these results to work for, starting from a certain n, you get all the sizes you can hope for. So definitely check out their talk, session 1A. It's really cool stuff. Okay, so now we can move to maybe the second way to look at our work, which is this is a work about PCPs. Okay, so Ron introduced them and gave us a lot of information about them. Let me just make sure we're all on the same page. So a PCP consists of a verifier that takes in a claim and wants to accept a correct claim or reject an incorrect claim. Now the catch is that the verifier can only, it also has access to some proof that proves the correctness of the claim. The catch is that it can only read very few bits of the proof. So even if the proof is like 1 trillion bits long, we'll only be able to read 3 queries of the proof, for example. And because of this restriction, we allow the verifier to use randomness. And this connection between the randomness and the queries, this is something that we'll look at much closer in a little bit. This is a notation that's commonly used to denote the decision of a verifier that it has access to a proof pi and samples a randomness r. So this is like either 1 or 0. Okay, the claim usually we think of as fixed in our context right now. So what do we want from a PCP? We want it to be complete. Correct claims can always be proven. We want it to be sound. So if you give the verifier an incorrect claim, no matter how you try to cheat, no matter what kind of proof you try to write, it'll always reject it very often. And the last aspect that we need from our verifiers is, much less standard than completeness soundness. It's called smoothness. So that means that in any proof, each location is equally likely to be queried. Okay, let me show a picture. So if this is our proof, and I plot here on the y-axis, what's the probability for, this bit, what's the probability that it's queried? Could it be the case that maybe the proof has 2 parts? The first one, I'm not sure what's going on there. But in the second part, bits are very unlikely to be queried. Maybe it's some junk padding or something like that. No, smoothness says, no, this cannot be the case. All bits are created equal. And this graph is just one flat line. And the reason we want smoothness is because it gives us tolerance. Okay, so if you start with a correct proof, a good proof that's accepted with probability 1, and you ruin it just a little bit, if your verifier was smooth, then you know that this new corrupted proof will still be accepted very, very often. That's useful. We'll see why in a little bit. So I'll now introduce rectangular PCPs. For this, we need to end up with rigid matrices somehow. So it'll be helpful if we take the proof, which was just an array, and we smoosh it into a matrix. Okay, so I'm not doing anything fancy here. I'm just taking a vector and thinking about it as a matrix. And for simplicity, let's think that the verifier only issues 2 queries, just to make things easier to talk about. So say the blue query, okay? There is this mapping, which like an indexing function I, that takes the randomness R and then maps it to a row and a column. Now in a rectangular PCP, we can partition the randomness. Let me do this again. So look at the randomness. We can partition it into 2 disjoint parts, okay? Such that one part, let's say the left part, completely determines the row of each query, and one part, the right part, completely determines the column of each query. Okay, so we focused on the blue query, but the same thing holds for the orange query and any other queries we may have. And this is just like a notion of locality and this mapping from randomness to queries, okay? It's like left half determines row, right half determines column. So that's what rectangularity is. And the main technical heavy lifting in this work is this proof of a rectangular PCP theorem. So we have a PCP for any language that is smooth. Like we said, we needed that. It's almost rectangular. I won't talk about this, but it's close enough for our application. And it has perfect completeness, constant soundness, constant queries, and the length is very short. Like Ron talked a lot about short PCPs, so this is kind of the same shortness. I won't be able to go into this, but it's comparable to these results that he mentioned, and it definitely makes use of them and kind of builds on them. Okay, so now that we know what rectangular PCPs are, let me try to, in the next few minutes, just maybe one more minute, I'll sketch out a connection between rectangular PCPs and rigid matrices. Okay, so basically what I'm going to say next is, you know how we thought of PCPs as matrices? Then the argument is that if this PCP was rectangular, then the matrix must be rigid. Why is this? So PCPs for what? We start with a language, which is the language from the non-deterministic time hierarchy theorem. So it's this language L, okay? It's unary, sure. And L has exponential length witnesses, but you can't shave even a logarithmic factor off of the decision time of L, okay? Now, let's suppose that proofs for L in that system that we constructed, let's suppose that they're not rigid, and we're going to decide L in time that's too good to be true. So that was a contradiction, and therefore these proofs must be rigid. And how do we do this? Well, if the proof was not rigid, okay, then what can we do? We're given an input, which is just some 1 to the n. And what we would really want to do is guess the proof and then verify it using our verifier. But a proof, right, this is an n times 2 to the n, so a proof would be at least 2 to the n bits. And that's way too much because we need to go into 2 to the n over n. We need to shave something off. So because the proof was not rigid, we can approximate, we can compress it, or we can approximate it with something compressible. Let's guess the compression. Okay, that's going to be much less bits and within our budget. And the next part, this is the last part, is to somehow use this compression that we guessed and the rectangular verifier to verify that the input was in the language. And here pops all these questions, which I won't be able to answer because our time is almost up. But one question is, wait, the compression was of something that was close to the correct proof. It wasn't the correct proof. So the answer is, you know, we had smoothness, we had tolerance, close to correct is good enough. But the second question, which is really the big question, is we have, you know, the verifier looks at proofs, which are rectangles, but we have like a compression it looks at proofs, which are matrices. We have a compression of a matrix. What do we do with this compression? It's unclear how to have the verifier interact with it. And the answer to this is where rectangularity comes into play. So if you take a look at the full video or the paper, we talk about this a bit more there. The last thing I want to say is that this whole argument that you just saw about a connection between PCPs and rigid matrices is definitely an instance of Ryan Williams's framework of how to get lower bounds from algorithms. And the algorithm that we use here is this fast counting algorithm for the number of ones in a low rank matrix. So this is also a crucial part, and it's really, really cool. That's it. That's all I have to say. If people have questions.
Yeah, we have time for a quick question.
Also, it's maybe a weird question, but a very cool result. I'm just wondering if there's any way in which you can think of plain old PCPs as rigid vectors. Is there some kind of way you can think of it that way?
Well,
I don't know what a rigid vector is, but maybe it's just
a rigid vector. To answer your question, let's start by thinking about how any vector is I mean, because I don't know what a rank of a vector is.
Right,
so
exactly.
Any vector is a matrix if you try hard enough. No, any vector just is a matrix. So what you're asking is maybe all PCPs are rigid and not just
no, because somehow PCPs are not, you know, as a definition, they're not natively matrices.
Right.
So I'm thinking if there is some like analog of rank for vectors, that would be.
I don't know if of such an analog. I do want to say something though. Maybe that's not your question, but I want to answer a different question. Maybe I do want to say that Josh Allman and Lijia Chen in that work 1 year ago, they definitely show that like basically some PCPs are rigid without looking with. They didn't like use any rectangularity. That wasn't a thing back then. So in that sense, yeah, like kind of some PCPs just are rigid, but to show this, they really need to manipulate the PCPs.
Right, probably the tensor structure.
Yeah, they do some bootstrapping and a bunch of stuff like that. So what maybe a takeaway message is like rectangular PCPs, they kind of make sense. Like it makes sense to look at a PCP as a matrix if it's rectangular. It's not just like some arbitrary looking at a vector as a matrix. There are some nice properties there.
Okay, let's thank Or, and let's have the next person set up. Ame.
Yeah.
Or I think you need to
Stop sharing.
Yeah, thanks.
Okay, let me quickly get started.
And Or there is a question for you, but maybe you can just answer it in chat. We have to move on.
Yeah.
Okay, can you see my slides?
Yes.
Oh, okay.
So the next talk is on the existence of algebraically natural proofs, and Aname is giving the talk.
Yeah, thank you. Thanks a lot. Yeah, so as mentioned, yeah, I'll be presenting my our work on the existence of algebraic natural proofs, and this is a joint work with Pirona Chatterjee, Mrinal Kumar, Ramya, and Ramprasad Saptashi, and all of us are from Mumbai. Yeah, so let's get started. So we are interested in computing multivariate polynomials for the next 15 minutes at least. Okay, so suppose you have an explicit polynomial f that you want to compute. So one way to do this is to just start with the underlying variables and some constants from the underlying field, and suitably apply additions and multiplications till you finally compute your polynomial. Okay, this whole process is equivalently represented by a directed acyclic graph or a DAG, which we will call the algebraic circuit for this polynomial f. The circuit has what we will call the size, and size of the circuit is basically the number of gates that are in it, which are basically the number of operations, additions and multiplications used. So once we have all these things, we get a nice complexity measure for polynomials. So for a given polynomial f, the size of f is just the smallest circuit, the size of the smallest circuit that computes it. Okay, and yeah, so for the purpose of this talk, we'll be interested in polynomials whose degree is polynomially related to the number of variables. Yeah, so as a result, efficient polynomials will be polynomials that have poly-size circuits. Okay, so if you collect all these efficiently computable polynomials, you get a class that is the algebraic P, or which is called Valiant's P, named after Valiant, right? And a good representative for this class is the determinant on n squared symbol, like the n cross n symbolic matrix. And determinant is just the usual determinant. And wherever there is a P, there has to be an NP. So there is a Valiant's NP as well, which is kind of the class of all explicit polynomials, if you will. And a canonical member of this class could be the permanent, which is like the close cousin of determinant, but it does not have the signs, and which is why we expect it to be hard to compute. Yeah, so the central goal of algebraic circuit complexity, or a central goal, is to find explicit polynomials that are not efficiently computable, right? And if we are lucky, we might find a polynomial that is in V and P that is not efficiently computable, thereby separating VP and VNP. Yeah, so this is the goal. We want to find explicit polynomials that are super polynomially hard. So where are we currently? And yeah, I mean, the best circuit lower bound is barely bigger than linear n log n lower bound, which is also tight, and is also quite old. Yeah, it has not been improved upon. On the other hand, we have a lot of like strong results in structured models, and these models are not important. What is important is that we have super polynomial, sometimes even exponential lower bounds against structured models, and yet we don't have, and they have not generalized to circuits. So a question is why? And something that might help us to decide why this is the case is the following observation that is kind of there in a lot of works. Yeah, and yeah, so basically the observation says that a lot of these results against structured models, they follow a certain template, right? So let's see what this template is. So yeah, so here is a natural proof strategy or a natural recipe to compute, to find lower bounds against any class C that you have in mind. Right, so firstly, we will need a succinctly describable weakness of C, and then we would want to find an explicit polynomial that is not weak in the above sense, right? So which will mean that H has to be outside C, right? So a typical instantiation of this recipe is as follows. So what we do is we find a non-zero polynomial, okay, that vanishes on all polynomials in C, right? So this is a polynomial that takes other polynomials as inputs. So how we are going to do this is by looking at coefficient vectors of these polynomials in C, right? So we have a non-zero polynomial P that vanishes on all of C. And because we want it to be succinct, we'll additionally also insist that it should have efficient circuits, but let's just work with poly-size circuits for now. Okay, and then because it has poly-size circuit, we will hope that that it might have an explicit non-root, right? We might be able to find an explicit polynomial on which it does not vanish. And yeah, I mean, if all these things work, then we have a lower bound, right? So this recipe or the strategy was further formalized in the recent works of Grochov, Kumar, Sachs, and Saraf, and FOCS, Pilka, and Wolf, which were independently uploaded a few years ago. Yeah. So let's see the definition. So now consider two classes, C and D. So C will be the smaller class. So let's say it's some subset of little n variate multilinear polynomials. Okay, and let's say D is a class of capital N variate polynomials, and capital N here is exponential in little n. So D can take polynomials in C as inputs via their coefficient vectors. Okay, so for such D and C, we will say that there are D natural proofs for C if there is a non-zero polynomial P in D, right, which vanishes on all the polynomials in C, right? So just to this thing, so this is exactly points 1 and 2 on the top right. Right, it's just instead of saying poly-size circuit, we are saying that it belongs to this class D. And note that this is essentially saying that the class D can somehow distinguish polynomials in C from random polynomials. Right? This is what we want. Okay, so since this is the template, the question is, and this is the template that we use to find lower bounds, the question is, are there such nice natural proofs for VP, right? So let's see what we have. So first of all, this all might seem really familiar, and it's for a good reason. So this is strongly motivated by the work of Rasborov and Dudich on natural proofs in the Boolean setting. So a similar thing was observed in Boolean world as well, that most of the lower bounds that were known, in fact, followed a template which was called the natural proofs framework. And then they showed that under a widely believed cryptographic assumption, which is that one-way functions exist, that there were no natural proofs for poly-sized Boolean circuits, right? Okay, so there we have a believable thing implying that there are no natural proofs for poly-sized Boolean circuits. So what about algebraic circuits? What about natural proofs for poly-sized algebraic circuits? So currently what we have is the following. So this came from the work of FOCS, Pilka, and Wolf, which we just mentioned. So there is some evidence against natural proofs for VP, right? So when I just say natural proofs without mentioning a class, it just means VP natural proofs. Right? So poly-sized equations, right? So what they showed is that when D is too simple, like some really simple models and really structured models in algebraic circuits, when it is too simple, it cannot have proofs for depth 3 circuits, depth 3 algebraic circuits. That's what they showed. But again, this is all about structured models, and yeah, and it only gives a weak evidence. So then again, the main question is still open. I mean, what do we have for algebraically natural proofs for VP? Right. So there comes our main result. Yeah. So yeah, this is the question: are there VP natural proofs for VP? And the answer that you can get after looking at our work is like they kind of exist for well-studied polynomials. So what does that mean? So here is the formal statement. So again, little n and capital N are exponentially related and so on. So what we show is that there exists a non-zero polynomial P on capital N variables, which is also in VP. So it's efficiently computable, right? Such that it vanishes on the coefficient vectors of everything in all the polynomials in VP over little n variables. Okay. So at this point, if I stop, this just means that there are VP natural proofs for VP. But sadly, I cannot stop here. Yeah. So what do we have? So this P vanishes on coefficient vectors in VP if they additionally also have coefficients that are just in plus minus 1 or 0. Right. So some things I want to say about this. The first thing is this restriction of the smallness of coefficients is purely on the polynomial, and it does not put any restrictions on the circuit that you use to compute them. Right. And even though it feels very restrictive, most of the polynomials we're interested in are, like, example, determinant and permanent that I mentioned. And in fact, it's hard to think of polynomials that do not have this property of small coefficients. Right. And secondly, this is a non-trivial equation P, right? So this P is non-zero on a sizable fraction of polynomials with bounded coefficients, with coefficients in plus minus 1, for instance. Right? So this is a non-trivial equation. So basically a one-line summary of our result is that efficient equations exist for VP as long as you're interested in small coefficients. Right? So yeah, small coefficient VP has efficient equations. Yeah. So yeah. So some other results that we prove are as follows. So we prove a similar theorem for VP over finite fields, and we prove analogous results for the other class V and P that we talked about. Yeah, and in fact, we just prove. I mean, a general recipe comes out of our work that if you have good enough fitting sets for your class, then you get equations for the small coefficient version of your class. Right. So, and I think if you understand all the terms used in this talk, then you can just. I mean, the proof is simple enough for you to reconstruct. Yeah, so that is it. So yeah, so based on all these things, right? I mean, yeah, so this is just purely my opinion. I think there is no strong evidence for or against the existence of VP natural proofs for VP, right? And yeah, which makes me think of a phrase that we have heard quite a few times in the last 2 weeks or so, is that this is too early to call, right? It's not neither here nor there. Yeah, so I'll just end with open questions, like just a few more seconds. Yeah, so it will be great if someone could prove or disprove the existence of algebraically natural proofs, like VP natural proofs for VP, and even under standard assumptions like one-way functions or any other assumptions in algebraic complexity as well. On the other hand, maybe one could extend our results and show that efficient equations exist for smaller classes, maybe formulas or so the constant-free version of VP0, but of course without the added restriction on the coefficients. Yeah, so that's all I wanted to say right now. Thank you. Do check out the longer talk if you're interested. Thank you.
Thank you, and we have time for a few questions.
So since you said later that you had analogous results over finite fields, does that mean that the result you stated at the start only applied like over the complex numbers, or what fields would it apply to? Like the first result.
So the thing, yeah, the mean result, right? Yeah, this one. Yeah. I mean, it works over. So the point is, yeah. So over finite fields, you don't have this added restriction on coefficients. Yeah, but this result, as I've stated, it is for, let's say, rationals or something. I mean, you don't need to go to complexes because this is there. But yeah, I mean, the circuits could use like arbitrary complex numbers and stuff like this. Yeah. So this is a result over complex numbers, I think. Yeah. I mean, I can say that. Yeah. Sorry, was that the question or?
Yeah. That answers the question. Okay. Thank you.
Yeah, thank you.
Any more questions? Do you want to say a few words about the heating set high-level idea of the proof?
Oh yeah, sure. I mean, yeah, good. Yeah. So maybe people who don't know what a heating set is. So heating set for a class C is basically a proof of like a non-zeroness for any polynomial. Suppose H is a heating set for C, then so you can see my cursor, right?
Yes.
Yeah, yeah, okay. So suppose H is a heating set for C, then it would mean that for any non-zero polynomial in this class, it will, at least one of these points will be a non-root for that polynomial, right? So this is a, yeah, so what we do is we basically use this property and turn this into a proof, right? So suppose I get a non-zero polynomial and I want to test whether it belongs to C or not. So what I want to say is if G vanishes on the entirety of the heating set, then it is definitely outside C because H is a heating set for C. Right, so that's what we do. So we take G, we evaluate it on all of the heating set. Then we do some negation. I mean, if it is non-zero, we make it zero. If it is zero, we make it non-zero, and then we just take a massive AND. Yeah. So basically, this definition of heating set, you can just use it as a proof. That's what we see. And yeah, so this AND can just be multiplication. What is the problem is this NOT gate. I mean, this NOT has to map all non-zero values to a zero value, which means it requires large degree over things like complexes and rational numbers and so on. Yeah, so for that, what we have to do is, yeah, so over finite fields, this has a simple solution. I mean, you can just do NOT by this Frobenius map, I think it is called. Yeah, but over characteristic zero field, it requires large degree, as I said. So what you do is you restrict coefficients and then you use Chinese remaindering. And I think I'll only say that much.
Thank you. So let's thank the speaker again. Thank you. And who's the next speaker?
That's me.
Oh, okay.
Can I start?
Okay, yes. So the next speaker is Vishu, and yeah, just go ahead. Thank you.
Yeah, okay. The title of my talk is a bit long. Let me quickly explain it. So we titled our paper SDIT, Symbolic Determinant Identity Testing is not a null cone membership problem, and the symmetries of algebraic varieties. This is joint work with Avi Vigdisson. So there's mainly three parts to my title. One is symbolic determinant identity testing, which some of you should be familiar with. The second part is null cone, which also a few of you, maybe a smaller set of you are familiar with. And the third part is symmetries of algebraic varieties, which all of you are familiar with, even if you don't like the words. Okay, so I'm going to start with a story that started maybe a few years ago. Well, okay, the real story started much longer ago from this particular algorithmic problem. So this algorithmic problem is called non-commutative rational identity testing. So the problem asks you something kind of simple. It says, I just give you some rational expression in some variables, which consists of some number of variables, addition signs, multiplication signs, and inverse signs. And I want to think of these variables as non-commuting, so it matters which way I multiply them. And perhaps what's more interesting is, unlike the commutative setting, if I give you a rational function in the commutative setting, you could write it as a polynomial, as a ratio of polynomials. You couldn't quite do that in this setting because you might have these things called nested inverses. So for example, in this case, if you look at this AB inverse A plus A, so that's the first term, and then there's a whole inverse, there's no real way to kind of merge those two negative inverses. So such a phenomenon is called nested inverse. But in any case, so the algorithmic question is, somebody hands you an expression like this. Can you tell me whether this expression simplifies to 0 or not? Well, we don't have much time, so I will tell you that this particular expression that I've written down actually does simplify to 0. And you might initially wonder if there's even a naive algorithm for this. And I don't think there's a naive algorithm to do this. So I guess the sort of basic question that you might ask in sort of a rigorous way is this problem even decidable? And of course, we know a lot more about this. So let me tell you a little bit about the journey of this problem. So this problem happens to be equivalent to this other algorithmic problem called non-commutative Edmonds problem. And this problem will take as input an M tuple of n by n matrices, x1 to xm. And you are supposed to decide if this formal linear combination, where these t1 to tm are variables, whether this formal linear combination is singular as when viewed as a matrix whose entries are linear expressions in the t1 to tm with coefficients coming from the entries of the xi's. And I want to know if, so I want to view these linear expressions as elements in this thing called the free skew field, which you should really think of as the analog of the free commutative field in the non-commutative setting. So the free commutative field would be just the function field in m variables. So if you like to think of it, you start with the complex numbers, you throw in m variables with asking for no relations other than commutativity, and you end up with the function field. So if you do the same thing without even asking for commutativity, you end up with what's called the free skew field. Now, I mean, it's a bit more complicated for me to explain in such a short time, so I will leave it to that intuition. So this particular problem, this non-commutative Edmonds problem, I want to slightly reformulate it, just because I like certain language better than others. So I want to think of it as membership in a particular set. And this set is going to be a subset of a vector space. This vector space is going to be m tuples of n by n matrices, which is this vector space V. And the set is going to be basically the set of all m tuples where this formal linear combination is singular. Okay? I have not said anything all that serious. I just said I'm just considering membership in the set. The set is basically the set of points which has a certain property. Okay, so but what do I really gain by making this formulation is something that is maybe not all that evident, but this particular set happens to be a subvariety. And so you could think of it in a more general context where you pick some subvariety of a vector space and you ask for the membership problem in this subvariety. Now, the subvariety could be given to you in many different ways. Subvarieties could be encoded by polynomials. They could be given implicitly by many other ways. And you might want to think of this in this larger context of membership inside a subvariety, an algorithmic problem, which is what it is. Now, what's so crucial about this particular subset is that it happens to be a special kind of variety, a variety that's called a null cone for the action of a particular group. And in this case, the action of the particular group is going to be an SLN cross SLN. SLN is determinant 1 matrices of size n by n. And on m tuples of n by n matrices, these things, one of the SLNs acts by left multiplication, the other by right on all of the m matrices simultaneously. So under this action, there is something called the null cone. So the null cone happens to be the set of all points so that if which you can take to the origin by applying group elements in the limit. So you, in slightly more formal terms, you take the orbit, which is all the points that you can get to from the point you started with by applying the group action, and then look at its closure, the topological closure, and see if the origin is in that closure. So that's what a null cone is. And it so happens that this particular really interesting set that's popped out of this problem of non-commutative rational identity testing after you've reformulated it enough number of times happens to be a null cone for this really nice action of SLN cross SLN. And this particular idea is crucial, even if not entirely evident in the initial formulations of in the initial papers themselves, is very crucial to give a polynomial time algorithm for this non-commutative rational identity testing problem. Okay, so based on that, given and I should attribute this to Garg, Gurwitz, Oliveira, and Vigdison, and Ivanios, Kiao, and Subramaniam, 2 different approaches, both using crucially the fact that it is a null cone. Now, given that we've got such a nice answer in the non-commutative setting, the natural question is to ask the question in the commutative setting. And so all I will do is I will take that same set, but change my property that defines the set from going from the non-commutative setting to the commutative setting. So now I'm looking for m tuples of matrices so that this formal linear combination is singular, but over the regular function field that we're all familiar with. Another way to think of it is it's a set of all m tuples of matrices such that any linear combination is singular. Okay, so now this also happens to be a subvariety of the vector space of m tuples of n by n matrices. And the question that kind of motivated this entire work is there an analogous story to the non-commutative setting? And so to be precise, the question is there a reductive group? Is there a reductive group action on this vector space such that the null cone is precisely the set that I'm looking for? The word reductive is a bit of a red herring. I don't want to get into it. It's a little technical condition that you need for several things to work. In particular, so the results that I told you about, the null cone for the left-right action, they can be generalized to the setting of reductive groups in a very natural way. And there are algorithms for null cone membership whenever there's a reductive group action. These algorithms are based on gradient descent and geodesic convexity and such notions. And there's a lot of work that's going into them and to figure out when they're efficient and what the trouble is and can we make them faster and so on. So perhaps the takeaway from the previous story is null cones for reductive group actions are great. So is this particular vector space, is this particular subset a null cone for a reductive group action? But also, why are we so interested in this particular subset? Is this subset is kind of very crucial to some of the central goals in arithmetic complexity. membership in this particular subset that I call singular tuples of matrices is just another way to say symbolic determinant identity testing. Okay, but what is this problem of symbolic determinant identity testing? Why is it so important? It happens to be important because a polynomial time algorithm for it will imply circuit lower bounds. This was a result of Carbonett's and Impagliazzo, I believe in about 2004 or something. And this is really a very serious result, because all we're telling you is you have to give a polynomial time algorithm for an algorithmic problem. And if you do, then you get these amazing non-trivial lower bounds for circuits that the community has been after for over half a century now. Now, the result that we prove in our paper is sort of disappointing in the larger scheme of things, in the sense that we show that there is no reductive group action for which the null cone is going to be this particular subset that you're looking for. So in some sense, what this really does is it tells us that there is a structural difference between the non-commutative and the commutative settings. And maybe we need to understand better why commutativity, something that we usually like and make use of, is actually playing spoil sport in this particular story. So I'm going to leave you with a couple of open questions. So the first one is probably the most concrete one. So somebody gives you an M tuple of matrices, and they tell you that its span has a basis of matrices whose rank is at most 2. With this additional information, can you then give a polynomial time algorithm to decide if this linear span contains an invertible matrix? So this sounds like several special cases of the symbolic determinant identity testing have been given polynomial time algorithms, and this sounds like the one that's just beyond all the ones that are known. And so that's maybe a good place for us to start a little bit. And maybe 2 questions that are a bit more, bit more high level. And so the second question would be to say, what if we go beyond reductive groups? If I let you pick whatever group you liked, could its null cone be singular tuples of matrices? Well, of course, that also presents a challenge with it, as to say, if it was the null cone for some non-reductive group, then what really would you do with it? Because the techniques that we have for reductive groups don't actually help you when the group is not reductive. So you would have, there'd be a lot more work to do. And the third question is maybe I've not said too much about this particular part of my work, which really goes more into the proof of our result than the statement itself. Is if somebody hands you a subvariety of a vector space, then how do you determine all linear transformations that preserve this subvariety? How hard is it to write down this particular group of symmetries, which is what we call it, which is the name I give it. So somebody gives you a subvariety in some intrinsic way, and you'd want to find out what are all the linear transformations that preserve this subset. So the subvariety, if it's not going to be a sub-vector space or something, so it's going to be some funny thing sitting inside the vector space, and you want to see which linear transformations preserve it. And we might want to understand the complexity of this algorithm problem. Yeah, with that, I'm going to stop.
Thank you. Do we have questions?
Visu, so in the first question, when the rank is at most 1, this problem is decided?
I think so. I think
this is a matroid intersection type question.
I believe you're at least epsilon close to what the point is. I don't remember this result exactly, but it goes back to a paper of Ivanyo's, Karpinski, Yuming Kiao, and Miklos Santa, I believe.
I see. Okay. I think it was, yeah. Okay, thank you. Yeah.
Okay, so let's thank Visu again, and Ankit is giving the next talk. Oh. uh, All right, so the next talk is on learning arithmetic circuits in the average case via lower bounds, and Ankit is giving the talk.
Thanks, Elena. Am I audible?
Yes.
So yeah, I'm going to talk about learning arithmetic circuits in the average case via lower bounds. And this is joint work with Neeraj Kayal and Chandan Saha. Okay, so arithmetic circuits or algebraic circuits, we already saw in Anaime's talk. They're a very natural model for computing polynomials. Basically, we have variables or field constants at the bottommost layer, and then we slowly build up the polynomials using addition and multiplication gates. For example, the circuit on the right computes the polynomial x1 plus x2 times x2 plus 1. So there are three fundamental questions about arithmetic circuits that are studied a lot in the literature. So the first is the question about lower bounds, where we want to find an explicit polynomial p which is not computable by small circuits. The second is polynomial identity testing or PIT, which is the problem of given a circuit, is the circuit computing a non-zero polynomial or not? And finally, the third one is of learning, or it's also called reconstruction, which is given a polynomial p, you want to find the smallest circuit computing it. So then between these three problems, there's several connections known. So these connections are known for general circuits as well as for specialized circuit models. For example, the connection between lower bounds and PIT, which goes via the hardness, algebraic hardness randomness trade-off. And then there are several connections known between lower bounds and learning as well. So what we do in this work is find new meta connection between lower bounds and average case learning. Okay? So what this meta connection allows us to do is to convert lower bounds for a circuit class C, which are of a particular type, into average case learning algorithms for this circuit class C. And so what do I mean by average case? So the algorithms should be able to handle most reasonable distributions on these circuits. And technically, what I mean is that the algorithms should work on certain non-degenerate inputs, and the set of degenerate inputs form a low dimensional variety, so that or a subsurface, right? So whenever you pick inputs randomly, they will not fall on this variety and will be non-degenerate. Okay? Yeah. So yeah, you should think of it as non-degenerate or most reasonable distributions. It should work. Okay? And I should say that this is a meta connection. So it gives a recipe for converting these low bounds into average case learning algorithms, but still a lot of technical work has to be done to complete to get the learning algorithms for a particular circuit class. Okay. Yeah. So what is the motivation to consider average case learning? So the motivation is that the worst case learning is just hard. Okay. So for example, even for the very special case of depth 3 circuits, the corresponding learning problem is tensor decomposition, which we know is NP-hard by result due to Hoster. And there are other hardness results as well. Okay? Yeah, and so to get beyond this worst case hardness of learning arithmetic circuits, you have to make certain assumptions. So yeah, I mean, there's this other line of work which makes designs algorithms which are parameterized by some parameter of the circuit model. For example, let's say they will assume that the top gate has fan-in constant or something like that. Okay, so there are many excellent worst case algorithms in that setting where you get some kind of a parameterized complexity. So I'm not going to talk about that because it's not it's kind of orthogonal to our work. Okay, so yeah, we try to go beyond this worst case hardness by some kind of a non-degeneracy conditions. Yeah, so let me give an example of such a average case learning. So let's consider this very simple circuit model where let's say you have a degree 3 polynomial and you want to write this polynomial as sums of cubes of linear forms. Okay? So this is just the symmetric tensor decomposition problem written in polynomial language. Okay? And yeah, so we know it's NP hard. That is given a polynomial P, it's NP hard to find the least such representation. Okay? Yet we can design meaningful algorithms for this problem. Okay, so one such algorithm is due to Yenrik from the 70s, and it's widely used in machine learning. Okay, so the formal statement is as follows. So if suppose the number of components in this sum is at most n is the number of variables, and the linear forms L1 to Ls are linearly independent, then given P, we can recover the Lis in polynomial time. Okay? So two things to note about this result. So there's some non-degenerate condition on the circuit that we're trying to learn, right? We assume the Lis are linearly independent, and this is a very simple condition to impose. For example, if we pick the Lis at random, then this will be satisfied. And the number of summands which this algorithm can handle is roughly equal to the best known lower bound we can prove about this model. And these two statements will be true for the kind of results we are also trying to get. Okay. Yeah, so there's some history of average case learning of arithmetic circuits. Yeah, so maybe I'll skip it. You can see the longer version. Okay, so informally stated, our main result for a specific circuit class C is that we get efficient algorithms for learning the following kind of circuit models, where you want to write a polynomial P as sums of powers of low degree polynomials. Okay, so you want to write P as sums of powers of Qi's, where Qi, the degree of Qi's is T, which is much less than the degree of P. Okay, so this is a generalization of the tensor decomposition problem, which is sums of powers of linear forms, right? This is sums of powers of low degree polynomials. And yeah, so two things I should say: the case P equals 2, okay, sums of powers of quadratics is already relevant for the problem of mixtures of Gaussians, and substantially new techniques are needed for the case T greater than equal to 2 compared to the T equals 1 case. Right? So this is because even the lower bound question is substantially different. Yeah. So here's a formal statement of the result. Yeah. So there's a randomized polytime algorithm that given black box access to a polynomial P, which can be written as sums of powers of low degree polynomials, it recovers outputs the Qis. Okay? So yeah, there's some technical assumptions needed. So of course, we cannot do it in the worst case. So Qis need to be non-degenerate. So I won't have time to define this non-degeneracy condition, but it suffices to say that this non-degeneracy condition is satisfied if each coefficient of Qis is chosen randomly from a large enough set. And then there's some technical conditions involving the N and D and so on. So the important things are that you should think of the degree of QIST to be constant and the field size to be large enough. Okay? And then there's some bound on the number of summands we can handle, which is comparable to the lower bounds we can prove for this model. Okay? Okay, so yeah, I won't have time to go into the technical details. Please watch the longer talk for this to see what this meta connection is. So yeah, quickly I want to mention a application to the problem of mixtures of Gaussians. Yeah, I only have 1 minute. So yeah, I mean, mixtures of Gaussians, I guess people are familiar with. Given a distribution, samples from a distribution D, which is a mixture of Gaussians, you want to find the components, and lots of applications and lots of algorithmic work. So yeah, the various kind of assumptions people try to make when analyzing the problem of mixtures of Gaussians. Either you make no assumptions, which is the worst case, or you make some separation assumptions, or you try to do smoothed analysis. And yeah, so what our work is most relevant for the setting of smoothed analysis of mixtures of Gaussians. So yeah, I won't go into the details, but yeah, basically, yeah, okay, so I'll just flash the slides. Basically, we have polytime algorithms in the smoothed case for mixtures Gaussians when we have diagonal covariance matrices. And the reason is that when you compute the moments, that the problem you get is sums of powers of linear forms or symmetric tensor decomposition. But for general Gaussians, we don't have such algorithms. And the reason is that the problem we get is sums of powers of quadratics, for which we didn't have good algorithms till our paper. Okay, so what our algorithm for sums of powers of low degree polynomials is the first step towards smoother analysis of mixtures of general Gaussians. Okay, yeah, so I'll only say that, and I think I don't have. Okay, I have some time. So we provide a meta framework for average case learning by lower bounds by reduction to a problem we call vector space decomposition, which I didn't have the time to go into, but please watch the longer version of talk. And yeah, again, we have to design some new lower bound methods to fit into this framework. Yeah, so there's some upcoming work, and then the most interesting future direction is on making these algorithms resilient to noise. That is, when you can handle noisy versions of the polynomials, which is relevant for the problem of smoothed analysis. Okay. Yeah, so open problems. So yeah, tensor decomposition is a very special case of learning arithmetic circuits, and it is useful in so many machine learning applications like mixtures of Gaussians and other probabilistic models. So it would be very interesting to see if there's some other probabilistic model problems which reduce to more sophisticated arithmetic circuit learning. For example, mixtures of general Gaussians reduces to sums of powers of quadratics. Yeah, and then we have lower bounds for other circuit class models as well. It'd be nice to do learning for them in the average case. And finally, it's very important to make our algorithms resilient to noise. And one concrete open problem is smoothed analysis of general mixtures of Gaussians. Yeah, thank you.
Thank you. Do we have questions? We have some time for questions. Can you learn anything if you have just maybe one large degree polynomial and everything else is low degree?
Oh, I see. Yeah, that's a good question. Yeah. So yeah, I guess it depends what high degree is. Yeah, so yeah, I should say that yeah, the algorithms we design are only for like sums of powers of constant degree polynomials, but yeah, we have lower bounds for much larger degrees of inner polynomials also, and the algorithm naturally generalizes, just that we don't have the analysis yet. Okay? So yeah, I think it should work for much larger T's as well. Yeah, just that we haven't been able to do the analysis yet. But the algorithm naturally generalizes because we have the lower bounds.
Okay, thanks. More questions? Okay, let's thank Ankit again.
Thank you.
And the next speaker is Swastik, or who's speaking next?
Hi.
Oh, hi. So can you set up?
Yes, just a second. Is it visible?
Yep.
Okay.
So our next speaker is Dan Corman, and he's going to be talking about proximity gaps for Reed-Solomon codes.
Thank you very much. And this is joint work with Eli Ben Sasson, Yuval Ishai, Swastik Uparti, and Chubangi Saraf, some of whom are also here in this talk. I will start by describing the a motivating problem for this result and our theorems. So our setting is we have a finite field FQ, and inside it we have an evaluation domain D of size n, and we consider the space of words which are functions from D to FQ, and inside it we have a linear code V. And our problem is basically to verify that given two words U0 and U1, that they are both code words, or that they are both delta close to the code, where here delta close is referring to having relative Hamming distance at most delta, so it's between 0 and 1 from the code. And of course, we can verify each of them separately, and we want to do that slightly better than two verifications. We would like to do that in one verification by instead, we will verify that a random linear combination of the two words is delta close to the code or a code word. And why will this make sense? This will make sense if U0 and U1 have correlated agreement with the code, which means that we're not only separately each delta close to a code word, but also they are delta close to code words on the same set. So there's a set D of size 1 minus delta on which they both agree with code words. If that's the case, then so does every linear combination of them. They will also agree with a code word on that set D. Or if they are just code words themselves, then every linear combination is a code word. But if we want to verify just this random element, then the question is the converse true? If it's true that when we verified a random element, we got something that is delta close to the code, does this imply that U0 and U1 are both delta close to the code? And the answer is yes. This is what improvement paper under certain conditions, of course. So we don't deal with general linear codes. We only deal with Reed-Solomon codes, which are evaluations of polynomials of degree at most k on the set D. And of course, it's entirely possible that U0 and U1 are completely arbitrary, but their sum is a code word or even zero vector. And maybe it's possible to arrange from them to be delta close for 5 values of z. So it's entirely possible that if we pick a random z, then by some miraculous probability, we picked one that gives us a code word or something delta close. So it will only be true that if we picked a random element, then and we got a code word, then we can be pretty sure that a miracle didn't happen. So just assuming there are no miracles, then we will be convinced that U0 and U1 have to be delta close to the codes themselves. And what this probability will be will depend on the parameters. The parameters that we have here are the field size q, the block size n, the distance delta, and also the degree of the polynomials k, or rather the rate of the code, which is k plus 1 over n. Specifically, the dependence that we have is that this only works for delta up to 1 minus square root rho. 1 minus square root rho is the Johnson bound of the least decoding radius of the code. It really strongly depends on the fact that there is a least decoding. So let's get to our theorem stated more formally. For two words U0 and U1 and the distance parameter delta up to the least decoding radius, we assume that the distance of the random linear combination of the two words from the code is at most delta with probability that is greater than epsilon where we take a random element. And this epsilon, we will get to it in the next slide. It's something small and explicit and depends on the parameters. If this assumption holds, then we have correlated agreement. That is, there is a subset D prime of D and two code words V0 and V1, such that D prime is at least of size 1, relative size 1 minus delta, and U0 and U1 agree with V0 and V1 on all of D prime. So this is exactly the correlated agreement that we mentioned before. In particular, if we have correlated agreement, then as we said, every combination of U0 and U1 must be a distance at most delta from the code. So what we get is that if we assume that this has probability greater than epsilon of happening, then actually this probability is equal to 1. So if we consider just the elements, all of these combinations together, they form an affine line of all combinations U0 plus ZU1. And what we say that this line features a proximity gap with parameters delta and epsilon, which means that if a random element is a distance at most delta from V with probability, then either this happens with probability at most epsilon or probability equals to 1. It can't be anything in between. It can't be that half of the elements are delta close to the code and half of the elements are delta far from the code. Either almost none of them are delta close or all of them are delta close. So what is this epsilon, this error term that some of the elements can be delta closed without all of the elements being delta closed? So we have two regimes for the theorem. Up to unique decoding radius, we can say that this epsilon is just n over q. So of course, for this statement to have any content, epsilon has to be less than 1. Otherwise, this just says something is less than 1 or equal to 1. And this will happen if q is at least linear in n. And going beyond the unique decoding radius up to least decoding distance, we get that q will have to be at least quadratic in the block size n in order for the theorem to have content. And there will also be some dependence on the rate and the distance, some constant that depends on them when they are both fixed. And of course, as delta approaches 1 minus square root rho, this constant will actually explode. And that's why we can't prove anything for the delta equals 1 minus square root rho case yet. And some generalizations also, we can replace the affine line and discuss instead a few other cases, which allows, instead of doing a reduction from verifying 2 vectors to verifying 1 vector, we can do a reduction from verifying L plus 1 vectors to verifying 1 vector by taking linear combinations in 2 different ways here, either with L coefficients and just random linear combination, and this gives us a random element of an affine space, or we can take just 1 random element and take its powers and take them to be the coefficients, and this gives us a parameterized curve of degree L. So for every coordinate x, this is a polynomial of degree L in Z. And also for these spaces, we also get the same proximity gap and the same correlated agreement result, that if we assume that a random element of this space is delta close to the code with probability greater than epsilon, then actually all of them are delta close to the code. In particular, all of these UIs are. Epsilon is the same for the affine spaces and slightly larger by the degree for parameterized curves. Let me review some prior work and applications. So as mentioned before, there was the idea by Rothblum, Vadon, and Bigelson from 2013, which was a seminal work for this. And we compare here all of these results by the upper bound that we get for delta. There are some other differences between these works, but we just consider that. So that paper had for that if you know that the random linear combination is distance at most delta, then it means that the 2 elements are distance at most 2 delta. So that's the doubling factor here. And the other papers went from delta to something slightly larger than delta, not much greater. So the next paper is by Ems Chazai and Nikita Subramanian, which goes up to 1/2 the unique decoding radius, when we have by Roth and Zemor up to 2/3 of unique decoding radius. And by Ben Sasson, Koparty, and Saraf, they went up to 1 minus cube root of rho, and later with Leo Goldberg, they went up to 1 minus cube root of rho. What are some applications? So there is an application which is very important to us, to soundness of communication efficient proof systems, specifically the Frye protocol, which is used in STARS and also in Agero, Aurora, and Fractal. And the soundness of this protocol is basically that for each query that we make, if we assume, for example, the 1 minus cube root rho bound, then we get for each query 1/3 log rho bits of security. And if instead we have the new 1 minus square root rho bound, then we get 1/2 log rho bits of security. So we simply need fewer queries to get to the same soundness. So that's a very practical improvement. And also there are similar applications to secure multi-party communication protocols, etc., etc. I will give a very brief sketch of the proof. The main idea is to use decoders. So decoders just get a word and the distance and give us all the code words that are delta close to this word. And for each Solomon codes, we have 2 decoders that we use. We have a Belkamp-Welch decoder that works up to unique decoding radius, and we have the Guruswamy-Sudan decoder, which is more complicated and works up to the least decoding radius. What do we try to decode? So we consider a word u0 plus u1 times z, where z is a formal variable. So this is just a linear polynomial in the variable z. And if we want to consider it as a word in some space, then this is in the space of all functions from D to the field of rational functions, which contains some things much larger than just linear polynomials, but that's the field that contains them. And what we know is that when we substitute values of z instead of the variable z, we get things that are delta closed to read Solomon code over FQ. And what we believe, what motivates us, is that this must be true because there is correlated agreement, because there are decodings which are correlated in the agreement with U0 and U1. This can't happen for just any two vectors that are delta close. The linear combinations will not be also delta close unless this was actually correlated agreement. And if there is such a decoding, then that means that V0 plus V1 times Z is a decoding of W. It's delta close to W. It's equivalent for this to being delta close and correlated agreement. And it's also a Reed-Solomon code over this field of rational functions. So we can run the decoder on W and hope to get something. Now, usually in order to prove that we get a decoding, we need to first assume that it's delta close to the code. But here we have a different assumption. Instead of assuming that W is delta close, we know that substitutions of W with various values of Z are delta close. But these decoders have algebraic properties, and in particular, they have commutativity property, that if we first try to decode and then we substitute values of Z, it's the same as first substituting values of Z and then trying to decode. Because we know the latter works, this allows us to prove with some algebraic tools that actually this W does decode as a word, which gives us the correlated. Thank you very much.
Thank you. Do we have questions for Dan?
Can you explain a little bit more about what is this commutativity of the decoding algorithm? What do you refer?
Okay, so I'll try to give a brief sketch of it. So basically for the Belkamp-Welch algorithm, which is much simpler than in the case of Goursami-Sudan, what the algorithm gives you is two polynomials A and B, such that A times W is equal to B. And then if you're actually delta close to the code, then you will know that actually A divides B, and the ratio is the code word that you're looking for. It's a polynomial of degree K. So in this case, you will have A and B, and you will be able to find them. And that also requires some proof, which you use the fact that for substitutions you get them, and they will also depend on the variable Z. But when you substitute values of Z, then you get A and B which divide each other, and the ratio is a code word that you want. And you have to prove that actually, even without substitutions as polynomials in both X and Z, then A divides B, and the ratio is a polynomial in X and Z, and also a polynomial of a form V0 plus V1 times Z, if the V's being of degree at most K. So there are many parts that need to be proved yet. But it all comes from the fact that when you substitute values of Z in these polynomials, then you know what you get.
More questions?
Sure, yeah. I actually have two questions. First of all, so is your argument sort of algorithmic in the sense that if they are correlated along the line, you can find the set D prime that sort of witnesses their correlation? Or is it, like, could you actually come up with an efficient procedure to do that?
So the argument is not really algorithmic. It's rather the algorithms give you certain algebraic items, objects, and use properties of these algebraic objects that usually give you a decoding, and you have to work a bit more to get them. You do use these substitutions, but you can call them witnesses, but it's basically you have certain, the main tools that you use is that if a polynomial vanishes at many points, then it's a zero polynomial. That's a pretty important tool, and that's why you need these many points to get that. For example, the higher coefficients are all vanish because they vanish at many substitutions. So that gives you a low enough degree, for example.
Yeah, see, so it's like the normal it's kind of like the normal sort of interpolation. Okay, and if I could ask one other question as well. So you listed some previous works. I was curious if any of those apply to any codes other than the Reed-Solomon code, or are pretty much all the works in this area restricted just to Reed-Solomon codes?
So I think well, definitely the first one is about linear codes, and and I think that some of these results are also for general linear codes.
What Reed-Muller? Reed-Muller sounds like the
RVW
next.
is for general linear codes.
Yes, and Swastik, do you know whether All of these are for Reed-Solomon codes or for general linear codes?
Yeah, everything is for general linear codes, except this one, except the current talks. And everything before was for general linear codes. And in fact, the 1 minus cube root rho is tight for general linear codes. And in fact, it's true for, it's tight even for Reed-Solomon codes where the block length is equal to cube. So, I mean.
Right, so we really have to use the fact that we allow the field size to be much bigger than the block length. And also, as far as open questions go, then going beyond this 1 minus square root rho is of course very interesting. But the absolute theoretical limit would be 1 minus rho, and that would be very nice to have.
Okay, thanks.
Dan, do you need any properties from the interpolation set? It can be an arbitrary set. Maybe you said it, but I missed it.
We assume nothing. I mean, you mean about the set that where these are close to the codes, or?
No. So your Reed-Solomon code is defined over some interpolation points.
Oh,
can these be arbitrary or?
Yeah, it's completely arbitrary here. For Fry, you use very specific sets. No, it's completely arbitrary.
Okay. Do we have more questions? I mean, we have infinite time. Okay, if no more questions, let's thank Dan again. And let's thank every speaker and every author in this session again. Thank you, everyone.